Normal distribution. Session prerequisites. Browse to our earlier material on random variables to know about PMF and CDF, covariance, joint probabilities and correlation. In preparation, please have the spreadsheet open on your computer and follow along. Maximum benefit guaranteed.
They all look like fountains to me. What are they?
These are monthly returns, Lisa, but they're in different sectors.
You mean they're histograms?
Oh yes, they are. Thanks for the correction.
There's nothing abnormal I see.
Yes and no. But first, you must understand what I mean by normal. Welcome to Statistics for Business 2. I'm Shankar and this is...
Liza. And I'm not your normal flower vase.
You bet. She's abnormally talented and she can ask me questions that run through your mind. We now begin with a series on the influential topic of normality. In this segment, I'll introduce you to the normal distribution and then talk about how normality emerges within a data set. Let's toss this fair coin 10 times. It would be naive to expect exactly n by 2 or 5 heads. Each time we carry out this experiment, we might get a different number of heads, right?
How about 9 heads? You're joking, right?
Even that is possible, but there's a slim chance of that happening. Now suppose we toss this coin n times. Empirically, the chance of falling heads is nh over n. So we have an error E, which is how much this fraction strays from the ideal probability of 50% or 1/2. E can be positive or negative, but as the number of tosses become really large, we can expect that this error E gets squished to 0. If we fix the number of tosses at n, but repeat the experiment thousands of times, then we get thousands of error figures. Here's a question. How will these errors be distributed? The guy in the picture is a French mathematician named Abraham de Moivre. He answered this question and paved the way for the most famous of continuous random variables, which we now know as normal. The underlying distribution for a normal variable has a density given by this expression. Now, business students, you don't need to bother with the exact expression. Just realize that a normal variable can technically take all values between minus infinity and plus infinity. Don't be too scared. There are two parameters that govern this density. They are mu or the mean and sigma or the standard deviation. If you are supplied these two quantities, then you know everything there's to know about the variable. As I always say, pictures speak 1,000 words. The tall one in navy blue is called the standard normal distribution, whose mean is 0 and standard deviation is 1. Compare the orange with the brown and you see that the only thing that's different is the location or mu.
The orange is like a hammered down standard normal.
Correct. Now tell me, Lisa, whose sigma is the highest?
Is it the green? That's the most spread out.
Fantastic, Lisa. As you can see, normal variables have a symmetric density about the mean.
Let me say this like an expert. The skew is 0.
Very few data sets will have a perfectly 0 skew. If we measure the skew, we must look for something close to 0. Remember kurtosis from our earlier segment? It tells us how crowded about the mean a distribution is. Normal densities have the property that their kurtosis is 3. Again, we look for approximate numbers if we are checking this. Chebyshev's theorem, remember? It shows us how important mu and sigma are for any random variable. Just knowing the two parameters will tell us where at least 75% of the data resides.
Says nothing special for mu minus sigma to mu plus sigma.
Yes, and you all know why by now. If our random variable were normal, then the containments get much more precise. Between mu minus sigma and mu plus sigma, we get nearly 70% of the data.
And 95% between mu minus 2 sigma and mu plus 2 sigma?
Right. This is one basic test of normality.